Welcome back to the curriculum. This is Stage 4, Lesson 27, and we're stepping into the world of static and default routes. These are the hand-coded routes you write yourself, line by line, telling the router exactly where to send traffic. Over the next few slides, we'll unpack when this approach is the right tool for the job, and just as importantly, when it isn't. Here's the path we'll take together. First, we'll break down static route syntax and look at the real difference between a recursive lookup and a directly attached next hop, a distinction that trips up a lot of engineers. From there, we'll cover the default route, the catch-all that handles everything you haven't explicitly defined. Next, we'll get into floating statics, which quietly sit in the background as backup paths. And finally, we'll touch on static routes in IPv6. And just as critically, the moments when reaching for a static route is the wrong call. So before we go deeper, let's set the judgment call. Static routes shine in small, predictable environments, fewer than 5 routers, a stub network, a default route pointing at your ISP, or anywhere you need to override what a dynamic protocol decided. They're also perfect when security demands that traffic follow one exact path. But the moment you have 10 plus routers, multiple paths, a shifting topology, or any need for automatic failover, static routes stop helping and start hurting. The rule of thumb: if it grows or changes, don't handcraft it. Now let's break down the actual command. The syntax is simple: IP route, then the destination network, its subnet mask, and finally, where to send the traffic, either a next hop IP or an exit interface. With a next hop IP like 10.10.20.5, the router does a recursive lookup, figuring out how to reach that address first. With an exit interface like JI01, there's no recursion, but the router has to ARP for every destination MAC. On point-to-point links, the interface form is cleaner. On broadcast networks, next hop is usually the safer choice. Let's put those two forms side by side, because the difference really matters in practice. With a next hop IP, the router does 2 lookups but only ARPs once for that single neighbor. With an exit interface, it's 1 lookup, but on Ethernet, the router will ARP for every destination it sees, which can flood your ARP cache fast. There's also a failure twist. If the next hop becomes unreachable, that route drops out cleanly, while an interface-based route stays installed as long as the link is up. So the rule of thumb: next hop IP for Ethernet, exit interface for true point-to-point, and when in doubt, go with next hop. Now, with that in mind, let's talk about the most famous static route of all, the default route, written as 0.0.0.00. That mask of all zeros matches literally any destination, which sounds reckless until you remember longest prefix match. Anything more specific in the table wins, and the default only kicks in as a last resort. It's how your router says, "I don't know where this goes, so send it to the ISP and let them figure it out." Without it, packets to unknown networks, basically the entire internet, get silently dropped. In the routing table, you'll spot it as S** 0.0.000 via your upstream gateway. Now here's a clever trick built right on top of that AD concept, the floating static. You configure 2 static routes to the same destination, but you tack a higher AD onto the second one, like the 200 you see at the end of that second line. Because the router always prefers the lower AD, only the ISPA route sits in the table. The backup floats invisibly in the wings. The moment that primary next hop goes unreachable, the AD1 route gets pulled, AD200 steps in, and traffic quietly shifts to ISPB. When ISPA recovers, it preempts, and the backup drops back to dormant. Simple, deterministic failover with 0 dynamic protocol overhead. With that failover pattern in mind, let's walk through a full reachability example across 3 routers in a line. The key insight here is symmetry. Every router needs to know about every non-directly connected network in both directions. R1 points toward LAN 3 via R2's near interface, R3 points back toward LAN the same way, and R2 in the middle needs entries for both LANs since each sits behind a different neighbor. Skip any one of these and you'll get that classic one-way ping that drives engineers crazy at 2 in the morning. Now, the same logic carries straight over to IPv6, only the syntax shifts a little. The command becomes IPv6 route, and since IPv6 is CIDR only, you drop the dotted mask and just append a prefix length. Your default route, instead of quad 0, is simply /0. 2 gotchas worth burning into memory. You must enable IPv6 unicast routing globally before any of this works. And if your next hop is a link local address, you have to specify the outgoing interface. Otherwise, the router has no idea which link that FE80 address lives on. With routes configured, you need to actually verify they're working, and there's a small toolkit for that. Show IP route static filters the table down to just your hand-built entries, while show IP route followed by a specific prefix tells you exactly how that route got installed, its administrative distance, and the next hop it resolved to. Then prove the data plane matches the control plane. A ping confirms reachability, and a tracer route walks you, hop by hop, so you can see precisely where traffic is going, or where it's quietly dying. Now, when verification fails, it's almost always one of 5 culprits. Your next hop has to be reachable through a connected route, or the entry just sits there inactive. You need routes in both directions. Forget the return path, and you get that classic half-working ping. Watch your mask carefully, because a stray 2FE5.255.0.0 will swallow far more than you intended. On Ethernet, always point to a next hop IP rather than an exit interface, or the router will ARP for every destination and melt your CAM table. And finally, save your config, or the reboot will quietly undo all your work. So let's pull the whole lesson together. The syntax is straightforward. IP route, network, mask, then either a next hop or an exit interface, and it lands in the table with an administrative distance of 1. Lean on next hop IPs for Ethernet. Save exit interfaces for point-to-point links, and remember that 0.0 or 0.0 is your catch-all default. Floating statics give you a quiet backup path by raising the AI, and above all, routing is a two-way conversation, so configure both directions on every router in the path. Keep this cheat sheet close. It's everything you need at a glance. IPv4 and IPv6 share the same shape, just swap in the prefix length notation for v6. Defaults are quad 0 or /0. Remember static routes, write in at AD1, floating statics sit higher around 200, and when something breaks, reach for show IP route static, then ping and tracer route to prove the path end to end. That wraps up static routing. Next lesson, we shift gears into dynamic routing with RIP and EIGRP, distance vector protocols that learn the network through their neighbors, sometimes called routing by rumor. If this lesson helped, head over to Dargslan.com or the YouTube channel for the full series. I'll see you in lesson 28.